So the goal for section 3 is to talk about how electrons have essentially their own address within the atom, and these configurations are important because they tell us how the atoms are going to react, how they're going to act in order to obtain essentially an ideal electron configuration. So we're going to go over 3 rules that dictate how electrons fill the different energy levels that we talked about in the previous lesson. So again, an electron configuration is essentially how the electrons are arranged within the atom, and ideally the atom is going to have the lowest energy arrangement. Again, with exciting electrons, we can see that the electrons will potentially go to higher energy levels. However, we're just going to be talking about the ground state electron configuration today, meaning that in the lowest energy state, what is the atom's electron configuration? So here is the diagram that shows us the order that the orbitals will fill. Notice how 1s comes first, and then 2s, and then 2p, and then 3s, and then 3p. You might expect 3d to come next. However, 4s has slightly less energy than 3d. So 4s, even though 3d is in the third energy level along with 3p and 3s, 4s is actually going to fill first. And you see that trend as we go up the ladder here, that the order that the orbitals fill is not necessarily matched up with the energy level that the orbital is in. For instance, 3s, 3p, 4s, 4p, they are in the same energy level as one another. However, 4s will fill before 3d. So the first rule we want to look at is called the Aufbau principle. Essentially comes from the German for building. We're kind of like building the atom from the ground up, meaning that when I fill those orbitals with electrons, they're always going to fill the lowest energy orbital first. So they're always going to go in that order that I mentioned going up this ladder. You're never going to see 2s filling before 1s in that ground state. The second principle we're going to look at is the Pauli exclusion principle, meaning that no set of electrons can have the same 4 quantum numbers. We can have electrons sharing the same orbital, which would mean they have 3 of the 4 quantum numbers in common. Remember, we have that main energy level, we have the type of orbital, we have the orientation of the orbital, and then finally we have the spin. Well, this Pauli exclusion principle is telling me that the 2 electrons in the same orbital are going to have different spins. And then finally, the third rule is called Hund's rule, which tells me that when I have electrons filling an orbital, for instance, we might be filling the 2p orbital, instead of putting 2 electrons in the first orbital, when I fill that up, I'm going to put 1 electron in this orbital, and then fill up the second one, and then fill up the third one. All 3 of these are going to have to be full before I start doubling up. I liken that to if you have a suite room in college, everyone's going to want their own room before you start having to share a room. So all the electrons, and we're only talking in one orbital. So for instance, the 3d orbital, all the electrons are going to fill up those 5 rooms essentially before they have to double up with one another. So how we represent an orbital and the spin and all this stuff is we are going to write a line for the orbital. So for instance, if I have the 1s orbital, I can write a line and then write 1s under it. And the electron is going to be represented by an arrow, whether that arrow is up or down. The only stipulation there is that you can't have 2 up arrows or 2 down arrows. So that what I drew there would be an orbital containing 1 electron. Here's an orbital containing 2 electrons. Like I said, those arrows, because of the Pauli exclusion principle, have to have opposite spins. So we see there that they do. And those lines, again, we typically label them with the principal quantum number and the sublevel. So 1s would represent helium, because that 1s has 2 electrons. Helium has 2 electrons. So that's orbital notation. We're going to typically write these electron configurations. You're usually going to see them written as electron configuration notation, getting rid of those lines and arrows, and instead we're going to write it as the orbital with a superscript. This should say 1s and then 2. That's not 1s squared. Some people think that that's an exponent. That 2 is just telling me how many electrons are occupying that particular orbital. So that indicates that there's 2 electrons in helium's 1s orbital. So my sample problem, again, let me fix this so that it is accurate here. This should say 1s2, 2s2, 2p1. So the electron configuration of boron is 1s2, 2s2, 2p1. How many electrons are present? Well, it's actually an easy trick to figuring that out. All I have to do is count the superscripts. 2 plus 2 plus 1 tells me that there are 5 electrons. Looking at the periodic table seems to verify that, as boron's atomic number is 5. And the orbital notation would look like this, where we would have 1s filled with 2 electrons. Remember, they have to be opposite spin. We have the 2s. Remember, s only has 1 orientation, so I'm only going to draw 1 line for s orbitals. Again, same idea. And then finally 2p. Here's where we have to remember p has 3 orientations, so I have to draw 3 lines for any p orbital. But the p only has 1 in this case, giving me my 5th electron. We're going to fill it there. Remember, if I were to add more, I would have to add them to the other lines before I double up on that first line. Whether or not I draw them up or down doesn't matter, as long as I don't have 2 ups or 2 downs sharing the same orbital. So moving on to the second period, we see that hydrogen and helium occupy that first main energy level, that 1s orbital. After 1s, we're going to see that the second energy level, the 2s orbital, gets filled next. And we do have this diagram here which might help you see that order. If you were to write out all the S's, all the P's, all the D's, and all the F's in this fashion, you can kind of draw hash lines through them, and you'll see that these orbitals fill in that order. There's actually a way using the periodic table. The periodic table is actually set up in a way that you won't have to really memorize that order. You can essentially just look at the periodic table and figure it out. And we'll do that in a second here. But then we see the elements of the third period. Once neon gets filled, we'll see the 2s and the 2p get filled for neon. And then 3s and 3p are going to get filled in the third period. And I'm going to pull up that periodic table to show you. So there's a couple good images here we can choose from. It's a little too small to see. Try this one. You can take a look here. So as you can see, this tells me all the different orbitals that can be filled up. I'm actually going to look up a different one. I want you to see the blocks. We can go to ptable.com real quick. We look at electrons. You can see the blocks. Notice how helium gets moved over here to the second group. And then this makes a rectangle here. These are all going to be filling up the s orbitals. Notice you can see my little electron diagram over here. You can play around with that and see how these different blocks fill. Notice everything over in this section is filling p orbitals. Everything in this section, we're looking at the d orbital being affected. And then this section down here, I can actually show that that is meant to go here. That F block technically goes here. So anytime you're in the 6th and 7th period, you technically have to cross the F block to get over to the D block. So that's a common thing that people forget. A lot of people want to say 6S followed by 5D, but you have to remember that 4F actually comes first. So when we look at the order that I showed you, remember, looks something like this: 1S, 2S, 2P, 3S, 3P, 3D. Or, I'm sorry, 4S actually comes before 3D. And then you'll see that order there. The table, if we look at it this way, you can see it goes 1S, 2S, 2P, 3S, 3P, 4S, and then 3D. And then we fill up 4P, and then 5S, and then 4D gets filled, and then 5P, then we come down to 6S, and then 4F, and then 5D, 6P, 7S, 5F, 6D, and then 7P. And then that's the end of the periodic table. You may have noticed that some of the, especially the D block elements, might have been filling in a strange way as I was dragging my mouse across. There are some exceptions to those rules. For instance, here, chromium, you might notice if you look at that 4s orbital, chromium, that's a lower energy situation for chromium to have all 5 3D orbitals. All 5 3D orbitals, rather than having that 4s fill. So there are some exceptions to the rule. Copper's in a similar state where it would rather have its 3D orbital filled than have the 4s orbital filled. So most of the time, it follows just in the order, and you can see the electron configurations up above there, written in electron configuration form. And I have another video that I'll show you. We'll do a couple worksheets to get a little bit of practice with this, because I know it's new. I know it's, especially if you're watching online, it's something it's hard to sort of grasp on your own sometimes. So we'll take a little bit of time to try to understand how these electron configurations work. So you might have noticed up above on the P table, you see there are configurations with a noble gas located there. There is a shortcut, because if you notice, it gets a little repetitive. When you're looking at the electron configurations, you're always seeing 1s2, 2s2, 2p6, 3s2. That order always follows the same pattern. So what we can do to abbreviate it is just take the noble gas that comes right before. So for instance, if I'm looking at fluorine, the noble gas that precedes fluorine is helium. So we can take fluorine and just, instead of saying 1s2, 2s2, 2p5, we can say helium 2s2, 2p5, because helium is essentially 1s2 for its electron configuration. That doesn't seem to save us much, but if we come down here to like iodine, you can see instead of saying 1s2, 2s2, 2p6, 3s2, 3p6, etc., I can just write krypton, because krypton encompasses all of that before 5s2. I can just say krypton and then come down to say 5s2, 3d10, and 5p5. So we'll look at writing that out here. Again, just remember those group 18 elements are the noble gases, and the noble gas configuration is going to refer to the outer energy occupied by those 8 electrons in most cases. So as you can see, we've got helium represented here with 1s, neon filling up the 2s and the 2p, and then argon filling up the 3s, 3p in the third energy level. We talked about the fourth period, how 3d is going to actually fill up before 4p. And you see that here in argon. And then potassium, you see that 4s fills up in the fourth energy level. And then in the fifth energy level, again, we see that 4d filling up before 5p. So let's try to write the electron configuration for iron, Fe. Fe, and let's bring this back to normal a little bit. Do that. So iron, we see that it is in the D block, filling up there, and it's in the fourth period. However, you have to remember that in the fourth period, the D block energy level is 3. The D block is always 1 less than the period number. And for the F block, these two are always 2 less than the period number. The S and the P blocks always match the period number. So going to iron, let's just start at hydrogen here. It'd be 1s1. When I fill these both up, we would call that 1s2. Coming down to the next row, it's 2s2, and then 2p6. Then it would be 3s2, 3p6, then we come down 4s2, and then it's, remember this is 3d, so 1, 2, 3, 4, 5, 6. So it's going to be 3d6. So when we write that out, we're going to see that it's going to look like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and we said 3d6. So again, if we look at the noble gas that comes before iron, we can shorten that. The noble gas that comes before iron is argon. Argon goes all the way up to 3p6. So all of this is argon. So I can just write argon and then worry about the fourth row, 4s2, 3d6. And these are both ways to write the electron configuration for iron. So So I'm going to go ahead and leave you with this sample problem to try. If you can write both the electron configuration completely and the noble gas notation for rubidium. Again, if you're a little confused, I do have another video I'm going to post on Canvas for you, but let me know if you have any questions.